Okay. All right. So for homework yesterday, you had a few problems. The first one, I gave you an equation, and you were supposed to check off the correct boxes that. Sorry, 1 second. So you're supposed to check off the boxes that showed what transformations took place. All right. So there's a few things going on here. I overloaded it just to see what you guys said. So first we have the negative that's in front of the 5. All right. So the negative tells us that we're doing a reflection.
Mr. Murray, you're not recording.
What? It says I'm recording. Is it not showing up on your screen?
No. Okay, I'm gonna leave and come back.
And okie dokie.
Yeah, it's showing that you're recording on my screen.
Okay,
So
maybe it's just a small glitch. Okay, so again, first we had the negative in front of the 5. So you had to pick which reflection that was. Is it good, Radesh?
Yeah, I can see it now.
Okay, cool. All right, so the negative in front of the 5, what did that tell us? Did we do a reflection over the x-axis or a reflection over the y-axis? I think you all picked the right answer for that one. Yeah, good. Okay, that part there. Okay, is a reflection over the x-axis. All right, so that was the first part. That's one of your check marks. Your second check mark comes from this +3 up here. All right, so just be careful here. I threw a lot of different options out there for you, okay, to try to intentionally confuse you. So just, if it helps, write everything down, all right, instead of just looking at it. So when we manipulate the exponent, okay, that's going to be either left or right. And our rule for this is it does the opposite. Okay, so when I'm adding 3, okay, that tells me I'm moving to the left 3 units. So I know that's a little confusing, but the way I like to think of it is, well, it's kind of counterbalancing. Okay, so it's moving left 3 units. So originally if I plug in, 0, I would get 1, right? 1 plus 10. But now, in order to get that 0, I need to shift my x to -3 in order to get a 0 as an exponent. Okay, so that's kind of one way to look at it. Again, if you have your own method or your own reasoning, okay, stick with that. And then this +10 on the outside, okay, when it's on the outside, it moves up or down. And that one follows common sense. So that one is up 10 units. Okay, so some of you had these two switched around, right? So I think some of you put up 3 and left 10. Okay, so you had the right idea, you just swapped places. So just be careful with that. Okay, for the next ones, you actually had to solve. Okay, so using the one-to-one property, right? So your goal was to find a common base, right? And again, common bases are usually prime numbers. So you're looking for 2, 3, 5, 7, things like that. So here we have 3 to the x plus 1. Well, 3, I can't break that down into, 3 is not, 1.5 squared or anything. So that's going to stay as it is. The 27 changes to 3 to the 3rd. Okay, so here we have the same base. So we just look at the exponents. X plus 1 equals 3. So your solution would be x equals 2. Right? And then, I said this last time, but you can always go back and check. Right? You plug in 2 2 plus 1 is 3. 3 to the third power. Yeah, that gets us 27. All right. Number 3, we had to do 2 parts. Okay. You had to change this 1/2 and then change this 32. So the 1/2, I'm going to do this in 2 steps, would be 2 to the negative first power. Like that. Right? And then we still have the x minus 1 as that exponent. The 32, well, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 32 is 2 to the fifth. So before I can forget about the base and just worry about the exponents, I got to deal with this. Okay? So we went over an example like this on Monday. When we have 2 exponents, right, a power to a power, we multiply. So I distribute this negative 1, so I get negative x plus 1, and then that'll be equal to the 5. All right, so we subtract 1 from both sides. Negative x equals 4. So positive x equals negative 4. All right, so we get the negative. We change those terms because we have the fraction. Remember, fractions get us negative exponents. All right, number 4 was a little more straightforward. It's more like number 2. All right, you only had to change one side. 8 becomes 2 to the third. This is already a base 2, so we're not going to touch that. Looking at the exponents, 3 equals 2x minus 1. We add 1 to both sides, and we get x equals 2. Oops. Yeah, there we go, x equals 2. All right, and then 5 was, I don't think we went over one like this exactly, so this one might have been a little challenging, but that's why it was the last one. I put it there to kind of to challenge you guys. All right, so there's 2 things that we have to do here. So I'm going to do it in a few steps. So we still have this negative x to the outside. That's going to stay there for now. Now, the way you do this, you can do this in either direction. All right. The first thing I'm going to do is I'm going to get rid of this fraction. Okay, so 1 over 9 becomes 9 to the negative first power. And I'm going to leave the 27 alone since I haven't done any, base changes yet. Negative 1 times x times negative x will get me a positive x. Okay, so 9x equals 27. Now, sometimes when you get to this point, it might be common sense, right? So if it was 9x equals 81, well, you know that x has to be 2, right? 9 squared is 81. But this one's a little tricky, right? 9 to some power gets me 27. All right, so let's deal with, let's do our breakdown. So 9, well, that would be 3 squared. So that would be 3 to the 2x. Okay, so it becomes 3 squared, and the x tags along there. 27, we saw that before, or earlier, or whenever, would be 3 to the third. So when I'm looking at my exponents, I get 2x equals 3. So when I solve, I actually end up with a radical exponent. I end up with a fraction, x to the 3/2. Right, and that brings me to one part. Let me do it on the notebook. Okay, so today we're going to take a look at a special base. But before we get there, real quick, I want to talk about radical exponents. Excuse me. So radical exponents, we just dealt with radical functions. A radical is anytime we have a fraction. Okay, that's just a. I'm sorry, not radical. Oh, rational, not radical. Okay, so our rational exponents, okay, like our rational functions, mean we have a fraction. Okay, so some number to a fraction exponent. Now, if we actually have to calculate this, okay, if you come across a problem where you actually have to calculate, maybe, I don't know, 27 to the 2/3. There's two ways you can approach this, right? What this is doing, anytime we have a fraction, just a fraction exponent where the numerator is 1, we can rewrite this, okay? What a fraction exponent actually tells us is that we are doing a root, okay, or a radical. So x to the 1/4 is telling me I'm taking the 4th root of x. Let me make that a little smaller, okay? If I had x, the square root of x, okay, we can rewrite that as an exponent as x to the 1/2. So if I'm dealing with something like this, okay, this part down here is telling me I'm taking the cube root of 27, and then I'm squaring that answer. Or we could do it the opposite way. I can square 27 and take the cube root of that. Okay? What's nice about this is both of these will get you the same thing. Usually, I like this way better. You do the radical first, because that simplifies things, and I don't have to worry about doing 27 squared, which will be some, large thousands, and then taking the cube root of that. Well, here, I know the cube root of 27 is 3, so 3 squared is 9. Okay, so anytime we see a fraction up here, just know that we can split it like that, okay, or the other way, right? So you can either do the base to the exponent and then take the radical, or you can do the radical first and then do the exponent. Right, so that's just one way to deal with fractions as exponents. Okay, any questions or concerns about that? I think you should have gone over some stuff like this in Algebra 2, but it's been a while since I've taught that, so I don't know if they changed things. Okay, so the last part for, I think the last part, let me double check. Yeah, the last part for exponentials that we're going to talk about is a special number called our natural base. Okay, you may have seen this on your calculator. Okay, it is the number e. Okay, so e is like pi. It is a irrational number. Okay, it goes on. It's a decimal that goes on forever. Okay, a rational number can be expressed as a fraction, right? So 2.5, that's a rational number. I can write that as 5 divided by 2. Pi is an irrational number because I can't write that as a fraction. The square root of 2 is an irrational number because there's no fraction, right? It's some repeating decimal that goes on forever, right? So e, I always forget this one. I know pi, but Okay, E is the number 2.71828182, and it continues with that pattern. Okay, and there's a few ways that this number comes about. Okay, like pi. All right, so in geometry, hopefully you learn that pi comes naturally from the ratio of the circumference of a circle divided by its diameter. Okay, no matter what type of circle you have, that's how they figured out the number pi, right? Back when, Pythagoras or whoever it was discovered the number. Okay, they measured circles, the circumference of the circle, they divided it by the diameter, and every time, every circle that they looked at, they ended up with 3.1415, blah, blah, blah. Okay, so that's a natural occurring number. It occurred so much in nature that they assigned it pi. Okay, so it's the same thing here with E. Okay, again, that's called our natural base. Because moving forward, wow, we already only have 9 minutes left. So maybe tomorrow, I don't know, we'll see. There's different ways that we come up with this. It's seen in finance a lot. Okay, if you're calculating things like interest. Okay, so either, if you take out a loan, okay, this is, a whole other lesson that you'll probably learn about in Dalton's class next year. If you take out a loan, you're borrowing money, you have to pay for that borrowed money, right? So there's a way to calculate what you owe the bank. But sometimes it also works in your favor. If you put your money into a savings account, then you're earning interest on that savings account, okay? And they use this number to calculate that interest, okay? Again, it occurs naturally. If I wrote this symbol, do you guys know what this means? A sigma. Did you guys go over that last year? Okay, what it means is a sum, right? It's a mathematical term. So if I wrote something like this, this is telling me to add all the numbers from 1 to 5, right? So if I wanted to write this out, 1 plus 2 plus 3 plus 4 plus 5, right? You would add them up. What is that? 15. Right. So, when we're talking about things like sequences and series, which, again, I don't remember if it was geometry or algebra 2, you're supposed to see this, but we'll be talking about it later on this year at the end of probably the third or fourth marking period. This is a nice way to kind of condense some larger things. So we actually get the number E from what's called an infinite series, right? So I add up an infinite amount of numbers, and this actually gets me E. Right? I don't want to spend too much time on that, but I thought I'd give you guys the kind of the origins of it. Okay. And I think it's really cool because, like I said, we're adding up an infinite amount of numbers. So this never stops. I'm adding 1 plus 1/2 plus, it goes on forever. But that does something what we call converging, okay, to our natural base E, which is, again, 2.71828, so on and so forth. So we have a function, f of x equals e to the x. We call that our natural exponential function. Right? So it acts just like any other base, right? So I can raise e to the second power. I could raise e to the negative fifth, right? If you have, what happened to my calculator? On the calculator, there is an E button, okay? If you use your phone to do your calculations, you can see, again, I have an Android, so I don't know. Okay, it's actually right here on the Android. But if you're doing it on an iPhone, usually if you turn your phone sideways, if you turn screen turn on, screen rotation, you get a whole bunch of new operations when you turn it landscape mode, and you should see the E button there, right? So it might look like this, E with the X. It might look like E with a little caret after it, right? So when you hit that button, right, you hit the button E, it types in E, and then usually it gives you a little space, and then you just type in whatever you need to after, right? E to the second. That would be E to the second. Okay. Now, there's not much we can do with this actual number right now other than just plugging it in. Okay. With the lesson that we're going to start tomorrow, I think, we'll see, this will start to play in a little more. All right, guys. Any questions about our natural exponential function? All right. So yeah, so like I said, there's not much to really more to talk about it than this, other than, if you want to maybe just plug in a few numbers and see what you get. Okay, just fool around with your calculator or on the computer or whatever, and calculate a couple of e squared, e to the negative first, see what you get. But tomorrow we'll continue with a new topic that is directly tied in with exponential functions, but it's flipped around. All right, guys.